difference. For video segmentation, for virtual background replacement, it's very good to minimize jittering of segmentation mask too. The second implant doesn't improve intersection over union significantly, but it helps to reduce jittering. Next slide, please. The general architecture of minor network proposing is shown on this slide. Here you can see FCNet. Maybe you will be surprised, but it's a sequential neural network with the point-wise separable convolutions with hard-switch activation function. Here you can see temporal consistency block. I downsample input prior mask and extract 8 feature maps from prior segmentation mask. For merging features from 2 resolutions, I use my tiny feature fusion model and combination with prior mask features. I do feature refinement, and at the end I do extremely fast image upsampling, tensor upsampling to segmentation mask. And it's work. Next, for the tiny feature fusion model, I use squeeze excitation block, but before squeeze excitation operation, I do point-wise convolutions to reduce amount of channels, because LCNet use very large amount of channels for low resolution, and without these point-wise convolutions, these operations will be not so cheap. The next slide, please. And for feature refinement block, I use some trick with the cycling for device convolutions. Next slide. I think that Wavelet decoder really works for this problem, because it helps avoid overfitting, and maybe it's regularization too. For example, I know that if we annotate validation datasets by 7 annotators, then we will got inter-annotator intersection is about 99%, and so we have some mistakes on our data waveling, and it can be a reason of jittering between frames, for example. Yes. For last function, I use combination of binary cross entropy, Jakarta loss, and Jakarta loss related by pixel probability. I boost weight of pixels that nearest to border of transverse mask. At least for data augmentation, I use various techniques as color jittering, brightness and contrast jittering, and for augmentation of the second input to emulate video stream, I use empty triggers mask. It helps to simulate first frame and avoid for overfitting on propagation of mask through previous frame. I want to use image encoder and use all the features from them. And I use some fixed transformations. And it's very important to use this distorted image self-prediction of the current state of neural network to avoid a problem of variable shift. Yes. Maybe you are not interested in using LCNet and lightweight encoders, but maybe if you want to accelerate your neural networks, you can find useful such tricks that I have already used for last 5 years. It's Bohush norm fusion with convolution. If you have convolution and Bohush norm, that for inference you can manage these operations in new convolutions. So Bohush norm will be free for inference. Sure, I use separable convolutions instead convolutions that was originally proposed in exception neural network architecture. But exception separable convolution recommend to use that slice point-wise convolutions without activation between them. Francois give such recommendation is in this article about exception and in his book Deployment with Python. My experiments show that if we want to find extremely fast architecture, we need maximization of some of nonlinearities. So I use activations between the slice point-wise convolutions too. And slice convolution used instead of convolution pooling, cascade convolution of small kernels is preferred to use large kernels, etc. Next, and results of my work. I have already shown that proposed solution outperform other publications with large amount of sophistication. Also, I know that using pre-trained backbone is very useful because if I use initially randomly initialized backbone, metrics is worse, and without prior input, also metrics feel small. Last 2 years ago, I used mobile network and virtual architectures. These architectures is not so fast as LCNet, but good too. Most popular NP-net is zero. Good by insertion over union, but it's not very good from the performance point of view, because utilization of CPU is much worse. Yes, results. It's segmentation results. You can see that using pre-trained encoder initialization, segmentation mask is much more consistency than when I use random initialization. So initially feature representation by CNet is useful. And the conclusion proposed neural networks runs much faster than minimal requirement, and the small utilization of CPU allows to reduce the rate of discharge battery on laptops and or mobile phones. That's very useful for long video conferencing calls. Next. And it was a short presentation of part of my work. I hope that extended article about this research will be published later in a journal that accepted for publication stationary results, because there are a lot of other tricks that also allows to improve segmentation results.
Okay.
That's all. Thank you very much.
Thank you for your effort. Have you questions? Any questions? Oh, if you, I have a questions about. Oh, sorry. Where is the about this slide, and you talked about image C sigma, but I don't understand what is mean green and yellow color.
For weighting of pixels before evaluating such a card was, we use average pooling with kernel sigma and type 1. It's blur of ground truth masks and using pixels where mask greater than 0 and less than 1.
I understand. It's something like a fuzzy region. Okay,
Yes,
thank
yes.
you. Other questions? Okay, more questions. We go. Now we go to next reference. It is Angelina Pashkevich, cloud motion detection in video by combining CNN and integral optical form. Sorry, I should change presentation. Wait a minute. Wait. Because we have translation to internet and it's necessary start. Okay. Next. Stay calm. Ну, либо громче, либо ближе.
They to distinguish between the groups of people and other objects in the videos, the directions of their movement, as well as the relations between the directions of this movement. Specifically, I define a crowd and crowd motion. Also, crowd motion parameters and features will be defined. Of course, I provided with algorithm of crowd behavior analysis using CNN and segmentation flow, and the results of conducted experiments will be shown. Next picture. Louder? Right, I'm right. So, crowd is a large group of people. Individual persons in crowd are seen to be connected. And as a result, any crowd seems to be a connected company. There may exist several crowds in one frame, and any crowd is a number of subgroups that composes this crowd. And subgroup is a number of people that compose this subgroup. It's of importance to know that any crowd does not keep its composition during time. It can split or join with other crowds. Next, please. Okay. A crowd, subgroup, a person, can be assumed to two main classes. Stationary objects are defined by their features and coordinates that are not changing their position, that are not changed during the time. And such stationary objects can be represented as a formal model too. Motion objects are characterized by the changing of one or more their basic parameters, such as shape, position, coordinates, or maybe size. So, motion. Next. All objects can be represented by the formal model 3. For the conclusions, person is happy to be detected object, but the crowd or subgroup is considered to be a single entity. And this
Sorry, can you write that down because it was connection. I'm sorry. Okay.
So, first conclusions, person is only to be detected object in the window. Crowd or subgroup is considered to be a single entity, and the area under this crowd or subgroup is considered to be occupied by individual particles. And while particles are moving, the crowd can reshape or move. It's possible to track for one crowd in the frame, where the subgroups with their particles go in the next frame, or vice versa, where the subgroups with particles go take off. Once subgroups of the crowd allocated to the previous frame or posterior frame, further analysis of the crowd can determine whether a normal behavior happens. And of course now the subgroups of different crowds in one frame can compose one big crowd on other frames. Okay. Motion direction is the main destination of the crowd motion. And let's divide OTP interval into zero equal intervals, and let's count the number of pixels moving to each interval. The interval with the most pixels in this interval is the main destination or main moving direction of the crowd. So, crowd directionality in the region can be represented as a number of pixels going to this region divided to the bands on some of the vectors of moving directions. Also, the value represented by the 6 formula is a crowd motion symmetry. And the global this value is 1, the most symmetrically crowd moves. Motion of the pixel can be just calculated as the length of the vector on the displacement of this vector divided to the time interval considered. And the motion inter in the region can be calculated as the sum of motion speeds divided to the number of the pixels in this region. Yeah. Let's talk about the algorithm of crowd behavior analysis using CNN and optical. The algorithm for estimating the movement of the people is based on the behavior of optical flow and motion vector maps, and it is applied to the videos from the cameras in public places. At the first stage, optical flow is calculated using CNN. In my case, it was like the next. The optical flow is calculated with a sequence of frames in the video. Then integral optical flow is calculated, and it makes it possible to reduce influence of the background and to obtain an area of the intense movement. Based on the integral optical flow, motion maps can be obtained, and they allow to describe the movement of the slots in each position line. So, if we have two sequential frames, we can calculate optical flow between these figures. We can calculate the optical flow between these two frames. But it's always is that two directions, the red and the blue one, are defined. But the objects are not clearly defined, and there is no clear background under the motions of crowds. When integral optical flow is calculated, we can see that there is a white background, and it is unambiguously determined. You can compare optical flows and integral optical flow. It is lighter, and the objects and crowd in general are more clearly defined. In general, we can find two directions of the movement. The right crowd moves from the left to the right, and vice versa. The left crowd and the right crowd moves to the left. The colors show that the directions are not the same. In our case, they are even opposite to each other. I will tell about that a little bit. Yes. For visualization of directions on the flow branches, a pixel density was chosen. Pixel density is the ratio of the grid of pixels to the whole number of pixels in the frame. Small density, there is a small density, you can see green dots and red arrows. Show the direction of the movement. Okay, so low density. Low density, small density leads to the great accuracy of the movement vectors, but it causes loss of pixels and the result a loss of subgroups. It's difficult to define subgroups. Next, please. When we use high density in the grid, as a result, we see and it makes vectors. Vectors small. You can see the vectors, but you can see that the grid covers mostly the whole screen, and it is easy to define any subgroups like this, like this, like this. This subgroup, etc. So, the direction of the crowd movement and the ratio of the directions of movement can be represented in motion maps. A map with a vector at each position, indicating the total movement of all vectors to this point, is called in-pixel comprehensive map. And a map where each vector represents the total movement of pixels from this position is considered to be an outcoming comprehensive map. The map can also confirm the direction of movement of the crowd towards each other. Look at this example. It's in pixel map, and in each point here, in any point in the right point here, and any blue point here. It means that the direction from this map is to the left, and the direction from this map is to the right, and it's to the left. So this pixels leaves this position in the right direction, go to the right position and go from the left position. And opposite, this crowd goes from here there and from here. We can see that they leave very from the right. So, as in the left scan shows that opposite of directions or maybe perpendicular directions, if it is possible. There is no example of perpendicular direction, but mostly opposite. So the last one. And conclusion. With the help of motion and flow maps, it's possible to distinguish between groups of people and objects. To distinguish directions of movement, distinguish objects of movement, parallel, perpendicular, opposite, etc. Neural networks help us quickly calculate optical flows, but the results are not clear, can be clearly defined. So, integral optical flow get rid of noise, and at the same time get more accurate boundaries of the objects.
Thank you for your reference. Maybe you have any question? Okay.
Possibly I missed something. How do you deal with this situation when one part of the moving object overlaps with another part, an object moving to the opposite side?
When they intersected, optical flow for the computer. Берет с переднего плана объекты и учитывает только движение, за счет репетиции. Если, наоборот, перейдут репетиции, грубо говоря, это будет потеря данных.
То есть вы потеряете с того, кто сложит?
Да, естественно. Потому что он, грубо говоря, будет перейдут.
Ну, на самом деле, не совсем так, потому что комбинация используется различного оптического потока. Получается у нас что-то типа ненамерно. То есть можно материале, но за счет разницы движения этих каст, которые мы берем, то есть информация складывается в тех каст.
Ну, это несколько потоков, либо арочного. Но в целом, если вот сделали любовь, то время было придется потому что по пикселю, говоря, пиксели имеют отношение к нему. И в этом проблема. На самом деле, что грубо говоря, точно так же, как если у вас какое-то следующее здание, и у вас объект движется, и, грубо говоря, заходит за это здание, эта картина на самом деле неправильная, потеряется.
А следующим кадром вы не поймаете, вот у вас идет человек сюда, а здесь велосипед проехал.
Последующий, я это говорю, вы это момент видите. Да, на момент видите, естественно, будет отражаться.
Ну, вообще это не трекинг, это поведение. Поведение будет происходить.
Ну да, задача, собственно.
No, we have any changes in our program because this record going through the end. And now the next record will be Vadim Matskevich for first random switch algorithm in neural networks training. Just waiting for because I'm working in like a supercomputer. Oh, you can start.
My first first report is fast random search algorithm in neural networks in next slide. Let's talk about neural networks in general. Neural networks are used for solving a wide range of applied problems, as we see. And neural networks can adapt to any type of data, which is understandable. And neural networks can solve problems which do not have rational solution. It means that we do not have a solution which works fast enough, or we can receive a solution with quality which is not acceptable for our applied problem. That's why we use neural networks in real life for solving applied problems. Next slide. But there are some problems. Before being applied, neural networks should be tuned or trained for solving the applied problem. But training requires a lot of data and computations. Training is an optimizational problem, which requires a lot of data and an objective function for optimizing. And the objective function is a neural network generalization ability. There are two general methods for solving any applied problem, any optimizational problems. They are gradient descent and random succession. Everything's okay? Okay, next slide, please. But it's the first time we use gradient descent because it's very fast. The conversion speed is about from linear to square. And we also require a low amount of computations. Because to measure the derivative of the objective function, we require a part of input data which is rather small. But the derivative function calculation is required, which is not possible for all applied problems and objective functions. And the second problem, when we develop, for example, a security systems, when the quality of obtained solution is critical, we can obtain a poor solution quality, which is not acceptable in this case. For example, we can start at the local minima, or we can stop in inflection points, and something like that by any reason. So this method is not reliable in this situation. And the opposite method is a random search. It almost converges to optimal solution in some cases, and has a low objective function requirements. We just need to calculate the objective function value, and this will be enough to apply this method. But it has a very slow convergence, in average is logarithmic speed. And the second problem, it requires a high amount of computations. To measure the objective function value, to construct the estimation, we require all training data to do so. So this is the main limitation of random search. But nowadays, computers becoming more and more powerful, so this problem becoming less and less significant. That's why random search algorithms becoming more and more popular nowadays. Next slide. Here is the proposed algorithm in my report. First step is to generate initial solution. And next, we perform iterations. We generate a new solution, then we perform a transition into a new solution or not, and then we check the stop criteria. Next slide. Training an algorithm initialization. You're too fast. Initial solution X. My report is significantly shorter than previous ones, so we have enough time for additional questions and something like that. So don't be worried about scheduling. Initial solution X0 is random. We can generate it in any way. It should be only correct solution, and no more limitations than this. Next slide. The most important part of the algorithm is new solution generation, which is crucial in this algorithm. First, we should split all tunable parameters into groups before the training starts. We split it into groups according to some logic. For example, they have the same variance, or the more important than that, then they have the same semantic sense. For example, the first group will be weights of a single layer of a network, and the second group will be, for example, parameters of neurons in a single layer. So they are connected semantically between each other. So that was an example. Then we generate permutations for each group of parameters. The length of permutation of each permutation is equal to the amount of parameters in each group. Then we choose A1, A2, and etc. AM parameters, which are parameters of the algorithm. And first A1, A2, and so etc. AM parameters of each permutation determines the indices of changing parameters in each group. Next slide, please. Then we have to generate and use parameters values. We generate a random uniformly distributed variable on a segment from minus Li to plus Li, and then we add this implementation to the current parameter value. Then we perform a transition. If the objective function value for a new solution y is bigger than objective function value for a current solution x, we decline. Otherwise, we accept this solution. Hence, the end of the iteration is a stop criterion. When the time for training is over, we stop our algorithm. Otherwise, we go to the next iteration. Please, next slide. But this algorithm is not fast enough, even with this reduction. We need to make a scalable modification to speed up the solution. How we can do this? Here is a classical hybrid input data for classical algorithm which was presented on the previous slide. And on the right part of the slide, you see the scalable modification for speeding up. When we have a big neural network, which consists of huge amounts of data, tunable parameters, and requires a big amount of computations, we have to reduce the amount of computations and single iteration. First of all, we made several copies of the input data, and then we shuffle the elements of data in each copy except the first one. Then, amount of copies is a parameter algorithm as usual. And then we split it in the equal by size groups. The amount of groups is equal with the parameter algorithm of the algorithm, of course. And then we calculate the objective function value on a single part of the input data. We change this part from after performing several amounts of iterations, which is also the parameter of the algorithm. We change these parts until we reach the end, and then we again begin from the first part, like a cycle. Next slide, please. This trick helps us to reduce the amount of computations in time equal to the amount of parts. Second, how about efficiency of this algorithm? Scalable modification can be used for training big data on big data sets as a gradient descent, because we significantly reduce the amount of computations. Second, convergence speed is between random search and gradient, because when we select the small vicinities of each changing parameter, we behave like a gradient descent. But if the segments are big, they perform like a random search, but because we decline all solutions which are worse than current, so it's significantly faster. The amount of computations is closer to gradient methods rather to the random search, because we significantly reduce the amount of iterations and the amount of computations as each iteration. And final solution quality is closer to the random search rather than to gradient descent in average, of course, because we cannot guarantee it. Next slide, please. Let's talk about experiments. An SDL10 dataset was used for solid and applied problems for image compression, colored image compression. Resolution was 96 to 96 pixels, and here the hardware which we used. We use the most common quality functions such as mean square error, peak signal to noise ratio, peak signal to noise ratio of human visual system, structure signal to image measurement, and of course training time, because our report is fast training algorithm. We used two most important algorithms in experiments: the proposed one and the most common and one of the most powerful gradient algorithms which are used nowadays. Follow the moving leader. As we see on the slide, when we fix the compression ratio is low, we have extremely the same time. So it is the same time with the gradient descent, which is incredible for random search. When we increase the difficulty of our problem, we slow down by 2.5 times. But we significantly outperform it in terms of quality, which is much more important nowadays, because computers become more and more powerful. and we have enough time to change. So that is it. Thank you for your attention. Any questions?
Okay. Thank you.
Yes. We are speaking about resembles in some extent kind of an evolution story. You said that there are only two main groups of optimization algorithms. Gradient methods or random search. But in between, there are multi-agent methods.
Like sequence methods,
like genetic algorithm, like more general evolution strategies when
general evolution.
But in computation, the main difference is that instead use state your best solution. You also do it within your groups. But it would be interesting to add to this table comparison with this set of algorithms, which is
yes, it will be my second report. Just wait. It will be. Yes, it will be.
Okay. Any question else? No, thank you for your attention. I propose little rest, and now Aleksey Miroevskiy is report recognition of building from online images. Let me start. Sorry.
Since about recognition users to set languages. The main focus of my work is to investigate methods and algorithms for recognition users on set languages and recognize the amount of values. The set consists of 40 images. The variable contains a rural area and also now the specific of the I use star images that allows us to detect mountain powers of buildings. Why? Because this working star satellite is to emit waves in high length waves that can pass through clouds and buildings floors. And when they reflect it, satellites say us how many flows on or how now image interpretation to increase the size of region dataset, I use rotation by +5 and minus +5 digits. This is my architecture model. You can see this usual YOLO iteration. Metric is IOU, direction over union. Direction over union is my metric to control the quality of now model training. For the first step, I use canvas efforts and associated matches. Magic was spent. Now you can see a graphic over training model. And for the third step, I will come to parameters. Now we see amount of magic that with the third step it increases up to 94%. Things like that. Now we can see recognition. Yes, it's without skyscrapers, but magics are quite well.
So, okay, we have very fast now about some images because understanding some images is really complex problem because building have many files and every file have separate shadow and use separation shadows, yes. То есть you separate shadow for different classes and such way you can recognition. This example of reports is this example how to organize a data set for increase the quality of neural networks. It's not changing neural networks, it's changing properties of data sets. Okay, have a question? Any question? No, no question. Well, next report. Next report. Okay. Next report requires Petrovsky, Rate-Distortion estimation of 2D non-separable fluid interbands based on quadratic interband for the two substance. Okay, too complex name. Yes. Okay, 5 minutes. Yes. Можно показать, когда цепками. We can go.
My report is connected to some special class of the transforms, which is called paraunitary filter bands. It's kind of linear transform that can be used in image processing, image compression, and etc. And this report is done by a PhD student. It's mostly the idea related to evaluate performance of such transforms, and moreover, we want to look more deeper into non-separable implementation of this transform, how it can become from separable version, from one-dimensional version, which applies to the horizontal and vertical components, to directly multi-dimensional. So usually we treat transform of image compression or video compression framework as a state-of-the-art. So the properties of such step is important, and later in presentation I showed generalized image compression framework, which is used for Rate-Distortion estimation of this transform with discrete Wavelet versions from GPEC 2000 just to evaluate the performance. Next slide. So usually we can discrete Wavelet transform at the same time can be treated as a filter bank. The filter banks which is suitable for image compression is critical non-symmetric filter banks with symmetric or anti-symmetric interposes for accurate border handling. So there exists some different types of such filter banks. For instance, we look at the transform that is completely reversible and suitable for lossless scenario. So this means that analysis part, synthesis part in that domain will give us one's matrix. So there exists some difference in such filter banks. For instance, while we talk about the perimetry, it's well known that a synthesis part is taken from analysis factorization part with inverse matrix operation. So next slide. So the ideas behind this research, more common ideas that unite this research, that if we work directly with two-dimensional signals and synthesize directly two-dimensional transforms, it will be suited better for instance, for code gain characteristics of filter bank and etc. So we have some motivation that these transforms will have better characteristics, but at the same time they give some problems. Next slide. So usually, while we're talking about the separable version of this transform, we have to set some orthogonal transform version, which we apply for the rows and then for columns. And if you combine it in one equation, it will be the following. While we apply for the input signal x, it's kind of some basic image, and we apply forward transform, and then in one direction, and then in another direction. So it's very easy to understand how it actually works. Next slide. But in the same time, we have some limitation in terms of describing non-separable transform in that domain, because we need to somehow express this direction separately. In literature, it's done by two directions. First one is to split the directional Z domain, like Zx and Zy, and other approach can be used without this splitting, but we have to set up some special operators that related to the different view of matrix as the row, and it will be more easier to synthesize this transform. So we just invent a graph TV or inverse TV. So this means that it will just different view of matrix. Next slide. So why we need it? We need it because in the following idea that we want to express different dimension in the same realization. So we just write our transform in the bigger matrix with these two dots in size n square by n square. So it's square size more than existing transform matrix. And we have to describe the permutation matrix that is actually transform separation in this row view of the matrix. So while we set up all these operators, it helps us to avoid some complex Kronecker products to do this matrix factorization. And next slide. So basically, what does it mean? If we talk about a 4-channel filter band, for instance, and apply it to the image, it will be means the following. So we apply it in the row and in the column next time. So this is quite similar to classical discrete Wavelet transform, but if we rewrite it in this following form, we need to put block matrix on the main diagonal with analysis filter bank, and then apply transpose separation in this row order. Next slide. So the case of the filter bank that we want to evaluate is related to the Quaternionic algebra. If you're not familiar with Quaternionic algebra, it's like an extension of complex number system with three imaginary parts, and which is important to remember that it's a non-commutative algebra, so you have different multiplication results from P q not equal Q pair. But this multiplication can be rewritten in orthogonal matrix, which combination of this orthogonal matrix can give us some orthogonal matrix that we want to expect, which is important for filter bank description. Well, in that domain, we just need to set the orthogonal matrix for a unitary system. At the same time, Quaternionic algebra here used only as a tool of describing orthogonal matrices, which is very relatively old idea and very common. So next slide. And if we apply these ideas to factorization of analysis filter bank and rewrite it in this two-dimensional order, we just take one-dimensional filter bank, so place on the main diagonal of the transfer function, and we will have this directly two-dimensional transform. Next slide. So how it actually works? It can be rewritten very simple. So this is an input image, and the left side and the right side is applied to the rows and to the columns. This is just an equation for easily to understand, and then we'll collapse it to the two-dimensional version where the input image represented as a row and filter bank transfer function represented as the square times bigger matrix here dot dot. And if we skip this complex equation, next slide. So we can synthesize is in the same way for every matrix that involves in the filter bank factorization, and this way can be much more easily described using Kronecker tensor product, but for simplicity it's shown as it is. Next slide. So finally, we can have this two-dimensional non-separable factorization of 8-channel pairwise image mirror linear phase unitary filter bank, which is based on the Quaternionic algebra. And next slide, it is the structure, how it actually look like. So here we see, so for bigger size and for easily to describe, this picture is related for the 4-channel filter bank, which on the input receive 4x4 little image. This is unrolled on the line vector, and they apply stage by stage directly in 2 dimensions. So as you can see here, we have these boxes. It's Quaternionic multiplication operators, which is described left to right multiplication. It's just a block that involves Quaternionic multiplication. Next slide. So while we change the structure of filter bank, we have to set some metrics that is related for the finding the coefficients of this filter bank. It's related to the unconstrained optimization, where we would like to put the constraints related to the code gain and find the quaternions which suits better. And the main point here that actually we have two versions of filter banks. One is related like 4-channel, which become system which have input as 4x4 little images, and 8-channel, which is directly input 6. It's 8-channel filter bank, so it's split. This is two-dimensional magnitude response. Can give us some brief information how it works. And the next one. So, okay, to develop transform a different way, we have to somehow compare it with existing ones, and the most easy way to provide such a comparison is to develop some simplified, generalized image compression model, which involves transform, quantization, and some entropy coding model. While we apply all these models in the same way for different transforms, we can say that we set this experiment in same conditions for different variants, and we would like to evaluate separable version of such filter bank, non-separable implementation of Quaternion-based filter bank, and compare it with industrial standards discrete wavelet transform from JPEG 2000 standard. And next slide. So here we set the bit rate, try to set the bit rate, and it's close to the 1 bit per pixel, half bit per pixel, and 1 bit per pixel, and to measure in terms of FSNR, structural similarity, and difference of the structural similarity for transform. First one is separable version of Quaternion-based filter bank. Second is synthesized non-separable version of this filter bank, and DVT 9753. So we would like to evaluate it in loss scenario. So we know that evaluate DVT transform 5.3 in loss scenario is incorrect way to handle it, but at the same time, transforms that we would like to develop is actually based on the ideas that it will be completely reversible in integer domain. So we would like to test it also in loss scenario, but originally it's developed for the loss. The next slide. So here we have rate-distortion curves called Rykhard delta. So it's like spline approximation of different bit rates and different results in case of some metrics. And here is different transforms. So first one is filter bank is separable version. Second is wavelength 9.7. And third one is non-separable version of such transform. And fourth is just for comparison, wavelet 5.3. We can state here that separable version of parameter filter bank is much better in all these scenarios, and this is related that the length of the impulse, equal impulse characteristics of the channel of such filter bank is longer, and frequency characteristics and somehow much better. So this way we can understand why it's outperform wavelet 9.7, but at the same time we put a lot of effort to develop memory-less, non-separable transform called 3D non-separable parameter filter bank, and unfortunately it relays not that good as we expect. Why this happens? This happens because we have discontinuity on the borders between the rows of these two-dimensional blocks, and it is work good and nicely in case of the lossless compression, and there is some issues where we put it in lossless scenario. There exists some limitation on this approach, so we have to somehow to predict these values, and this did change the original idea, which related that we want to go to the multidimensional to avoid accelerometry. So that's all. And next slide is similar rate distortion curves for structural similarity, and they show relatively the same results. And the last slide will be conclusion. So general ideas that is related for our development of such non-separable transform is the base of the parallel pipeline architecture that can use for directly two-dimensional signals without auxiliary memory, with some additional complexity. But there exists some limitations in case of the lossy scenarios. So my report is over.
Okay, thank you for your report. In my opinion, it's interesting direction of science because it's real alternative for machine learning or neural networks, because filter bands allow to extract key features, and if you know what is properties of our case or of our K in image in signal, we can use it for as programming. And other important application is cost-free transform, because we can improve our processing by improve speed. It's should work more faster than traditional neural networks, and I think it's so interesting topics. And maybe you have a question, please.
I have a short question. For GPEG 2000 and for Wavelet transform, it is common to use a hierarchical system. And your system seems to be uniform. Did you try to extend your approach to a kind of hierarchical?
How to say this? The experiment that we would like to set up, we want to put this transform in the same channel numbers. If we go hierarchically, we make this tree which give us different dimensional resolution, and of course, if we treat it as a magnitude responsive filter bands, like more narrow set bands, and of course, this will improve the results. But transforms that we compare basically have from the first version it's 4-channel or 8-channel. So of course it's possible to do it hierarchically, but it means that we have to do the same tree for Wavelet transform. So we have to extend on the each lower number of channels. And for simplification, we would like to set this limit. So this is not industrial image product. So this is just an experiment for evaluation.
Okay, any question? The next, thank you for your report. The next report will be Vadim Matskevich about neural network software technology, triangle on random section and gradient descent principles. Okay. And, Ja sobie konstatuję.
I second, what is neural network software technologies trainable on the random search and gradient descent principle? This report is a compilation of over 4 previous reports, but some of them lasted more than half an hour, and it also contains a new material, so it will be very interesting. This next slide. Introduction, of course. Neural networks are used for solving a wide range of applied problems. There are a lot of frameworks for neural network training. You will ask me why there are so many. Because there are a lot of applied problems which are solved with the help of neural networks. And we need tools for automatization of problem solution. Next slide, please. But neural network before training should be tuned and trained as in the previous one. So it's nothing special here. Training requires a lot of data and computations, as we know. But modern frameworks have a lot of implemented optimizers inside. But modern frameworks support mostly gradient methods, but not a random search. That poses a serious problem on next slide, please. As we see on the slide, the main problem of gradient methods is poor solution quality in some cases. Because we cannot reach an optimal solution, we cannot guarantee that with gradient descent. And the second problem, not all objective functions have a derivative. But random search methods can converge to optimal solution, and the only requirement is we have to obtain, to measure, to evaluate the objective function value. But it is very, very slow. It's logarithmic speed convergence. And the second problem, a lot amount of computation for objective function value estimation. But nowadays computers become more and more powerful, so this problem became less significant, and random search became more and more popular. Next slide, please. Here is the proposed framework. It was implemented in C++ with OpenMP and OpenCL libraries. Supports different neural networks architectures, supports a wide range of different training algorithms, has multi-level polarization implementation, and has a lot of settings for training, which will be interesting, non-trivial, absolutely non-trivial. Next slide, please. First is architectures. Multi-layer perceptronics supplied, convolution layer, pooling layer, restricted personal machines of Gauss-Bernoulli and Bernoulli types are supported also, and autoencoders. Very important note, the composition of last two types of layers is allowed. It means that when we construct huge, deep neural networks, we have a very big amount of training tunable parameters. So we can easily apply a decomposition of layers to reduce the amount of tunable parameters to avoid a dropout technology during the training for random search, which is very critical. And deep neural networks based on these types are also supported, which is important. Next slide, please. Next slide. Okay, let's talk about optimizers in the framework. It contains well-known single gradient descent, momentum gradient, adaptive moment, follow the moving leader, which are the most powerful nowadays training algorithms from gradient descent. And we have 6 random search algorithms. Slow annealing, which was presented earlier, scalable modification from the previous report of this annealing method. Annealing, which means Poisson annealing scheme. And the kinetic algorithm, and scalable modification of kinetic algorithm, and which was called hybrid or fast random search algorithm, and its scalable modification. All of this algorithm will participate in the experiment. Next slide, please. We use a 4-level polarization technique to improve the speed of training. First level is virtual computational devices. It means that we can train several neural networks at the same time on the single computational device. It helps us to reach up to 20% performance training. And we also use a neural network composition where it is possible, because they're completely separated from each other. They're completely independent in data, in computations, in communications, because they form a single layer of a network. So they can train separately on different computational devices without any troubles. The second level of prioritization in CPU, GPU annealing prioritization. It means that when we use a GPU, we also have a CPU on the computer, at least a single core for synchronization. We can use it for calculations during the training, which were discussed in the previous reports. And this technique can be used only with annealing and fast random insertion algorithm, which we call greedy or hybrid micro-quant. The third and the fourth level of prioritization were caused by matrix multiplication, block matrix multiplication algorithm, which is well known. These levels are extremely important on GPUs rather than CPUs. The third level is data blocks are distributed between working groups, which is quite common. And the fourth level is single blocks elements of the matrix are distributed between threads of working group. It helps us to avoid an imbalanced load of each core of GPU. Because GPU has over 1,000 cores, it's a big trouble to load them all at the same time and with the same load amount of computations. But on the CPU, maybe the third level will be enough. But we use the third and fourth level also for CPUs. Next slide, please. This is the most interesting part. The amount of CPU threads being used can be tuned, which is not a surprise. The second is much more interesting. The amount of GPU cores being used also can be tuned. We can also tune a lot of settings of the GPU inside the framework. We can tune, for example, the amount of working groups, the amount of cores being used, the size of working groups, the amount of working groups, virtual device multiplicator, which helps us to reduce the amount of neural networks on the single GPU, for example. We can also set another settings of GPU, which is not discussed here. The third parameters are splitting neural networks into parts, neural network training, by layers and by time. The first means that we can train a single layer of neural networks without touching another ones. We can train a single layer of a neural network, save on the computer, and later perform the training of another layer, and the trained layer will be loaded automatically. We can also measure the time of training. We can reduce it just to set the amount of time for training each layer. The most important feature of this framework is that we can stop our training and continue from the same point. It means that if the computer is low powered, we can just set a small amount of time for training a single layer, set a new training option, and then we resume our training with the option continue training, and training from the point where we stopped in the previous one. It helps us to avoid problems with a small computational power. We do not reduce the training time, but we can increase the quality when we cannot train without stops. Next slide, please. This is the most interesting part of experience. Let's talk again about image compression of color images. A stereo data set was used. Image resolutions are 96 by 96 pixels as usual. The compression ratio is 0.75 bit per pixel. As we see on the slides, almost all interesting algorithms were compared. As we see on the slides, there are many interesting facts. First, between annealing and batch annealing. Scalable modification should speed up our training, but it's not in this case. Why? Because annealing methods, according to the hijack theorem, reaches the optimal solution at the infinity amount of iterations in probability. So scalable modification helps us to perform more iterations at the same amount of time. This helps us to reach high quality, as we see on the slide. Not significantly, but high. The second interesting fact that when we use a genetic algorithm, we turn a scalable modification and we reduce the training time almost in 2 times, because we reduce the amount of computations in a single iteration, because we use smaller amount of data at each iteration. The third pair is a hybrid or a fast random search algorithm, which we call gradient in this time and in framework, and its scalable modification. As we see on the slide, the training speed is almost the same, but we have more iterations, so we can easily increase our segments when we generate a new parameters value. So we can increase the session space with saving the training time. It helps us to cover bigger solution space and helps us to find better solutions in terms of quality. As we see on the slides, all random search algorithms significantly outperforms gradient methods, but they are also more than 2 times slower, even the fastest one, than gradient methods. But why is the difference in quality so big? It can be explained with the second layer of neural networks was a restricted Poisson machine of Bernoulli type. Bernoulli data is not smooth enough, especially for derivatives. So random search becomes significantly better in these cases. The more difficult we properly resolve, the better random search outperforms the gradient methods. And that is all. Thank you for attention. Next slide. If you have any questions, please ask.
Okay, thank you for your efforts. Maybe you have questions? No? Okay, if we have any questions, also have any questions, we can go into our last report. It's thank you, Vadim.
I hope you enjoy.
The next report, D9D. The name is based on big light yellow tree multi-page detection. Sorry. Where is the disk? Maybe it's not work. I don't see the presentation. Okay. Okay, we have some technical troubles. Now, I'm so sorry because it's not revived here. Because doesn't record this presentation. Thank you. The first. Wait 5 minutes.
Good afternoon. My name is Timothy. My talk about based on weak lines Euro 3 my text detection. Next. We can look this photo. You can understand based on my experiments focus on 5 lines in detection. Such as dark lights, and this photovisor and its production. I want to use my model on the very finite prediction, try to like mode 1 more recognition more times, and I improve and some way like in guidelines have some outlines, but these outlines are more exposure. Next page. So I do experiments. Let's imagine is original imagine, and then I try to imagine enhancement, like photo outlines exposure. This can like the photo information, potential information, and show more. Finally, I use enhancement.
It's clear maybe because for your solving.
You also solve this problem. What problem? In pipeline, there's more types. I choose use famous models. Makes the details of the imagine more problems, and then use the full model to recognize the targets on the verified lines conditions. Next page. And I have divided 4 parts. So each preparation builds congregation. And this is the issue. I need to let model more suits 5 lights communication. And I use software tools to reduce stretching or aroma of the imaging. And use this way, and I have collected 20,000 imaging data on the different lights. So about the predict filter model. I choose one sharp filter. Why I choose this? Because this can enhance the outline clarity and details image. But we need to know, we need to eject this parameter, because oversharpening lets the photo unrealistic, and we have some judge X. And this is second filters. This can help model help to imagine clear photovisor and delete some noise, image noise. Use these filters. Finally, I will predict filter parameters. So I use before the formula and the label. I fill in the loss formula, and then I create filter parameters predict model. This can help. This have other Euro model very quickly. So I don't want at my model that the Euro speeds less. So I use non-something. Non-something can let the image have low resolution, and this can help to speed, not too slow. And to follow, we can follow image 1 original photo. Image 2, this photo after the filter eject we can see outline already very clearly, and use this photo into the U3. We can get more and more. We can get more on the very wide license. You can recognition more targets. So this use this filter models useful. This is just introduce U3. Okay. There have some comparative analysis of model. The blue lines is filters compared with the Low-Latency models. We can look comparison Low-Latency and those more low just after 200 periods. But very important about comparability. Also, blue lines is filters compared with Low-Latency models. Finally, after 200 iterators, we can find these models are more good than U3, and accuracy rates bigger than 5% loss. And this is very helpful. U3 on vital lines conditions. And finally, we get conclusion and use U3 and compare filters help us to recognize vital lines.
Thank you. Thank you for your efforts. And I'd like to say that this work corresponds to high contrast low vision and DOT use YOLO like as adaptive filter, as I understand, and take increasing of contrast about 77%. Well, maybe you have question? One question? It's will be it's was last reference in our section, and now I finished this section. And I thought it's very long section, most long section in our conference, and I propose now in our next section to start at it's 3 o'clock. I invite you on the section. Thank you for your attention.